This video is supported by the NDLR and the Department of Mathematics in NUI Minute. In earlier videos we talked about what it means for a sequence to converge or diverge. And in those videos we said that in order to determine whether a sequence converges or diverges, we need to calculate the limit as n tends towards infinity. But sometimes that limit is difficult to calculate and we need to employ some other method in order to work out what that limit is. One of these other methods is to use something called the squeeze theorem, or what's sometimes known as the sandwich theorem. So we'll begin with a statement of the theorem. If the limit as n tends towards infinity of bn equals the limit as n tends towards infinity of cn equals L, and there exists an integer n such that bn is less than or equal to an is less than or equal to cn for all n greater than n, then the limit as n tends towards infinity of an is equal to L also. So we'll illustrate how this theorem works by having a look at an example. And the example we're going to look at is the sequence an, where the n term is given by sine n all over n. And as usual, I want to determine whether this sequence converges or diverges. So if I'm going to use the squeeze theorem to determine whether it converges or diverges, I need to fulfill the conditions of the theorem. In other words, in particular, I need to set up an inequality that looks like this, and also I need for the limit as n tends towards infinity of bn to be equal to the limit as n tends towards infinity of cn. So let's begin by having a look at the inequality. Well, what I need to do is set up an inequality with an in the middle, where the n term of an has to be bigger than or equal to the n term of bn, and also that the n term of an must be less than or equal to some other sequence cn. Okay, so first thing I'm going to do is I'm going to consider the trig function sine n. And I know that sine n is always greater than or equal to -1 and less than or equal to 1. But we're not dealing with sine n, we're dealing with sine n over n. So what I can do is divide everything by n. And I know I can do this without affecting the inequality because n is bigger than 0. Okay. So with our inequality in mind up here, what we've got in the middle is an, and it would seem reasonable to call this bit bn, and then to call this bit cn. So now we've got the inequality bit sorted. The next thing I need to do is, I need to check, does the limit as n tends towards infinity of bn equal the limit as n tends towards infinity of cn? Okay, so let's do that next. So let's calculate the limit as n tends towards infinity of bn. Well, bn in our case is -1 over n. And using our rules of limits, I can take this minus sign and bring it outside. So I get minus the limit as n tends towards infinity of 1 over n. So now, as n gets bigger and bigger, or as n tends towards infinity, 1 over n is going to go towards 0. So minus 0 isn't going to make any difference. It's still just going to go to 0. Okay, so that's that bit taken care of. The next thing I need to do is to calculate the limit as n tends towards infinity of cn. So let's do that. So in our case, cn is 1 over n. Okay, so we've this bit calculated already, we did it over here, but just to remind you, as n tends towards infinity, so in other words, as n gets bigger and bigger, 1 over n is going to go towards 0. So just like we hoped, we fulfilled this condition up here. We've got that the limit as n tends towards infinity of bn is equal to the limit as n tends towards infinity of cn. In our case, both of those limits turn out to be 0. So now we've fulfilled all the conditions of the squeeze theorem. So therefore, by the squeeze theorem, we can now say that the limit as n tends towards infinity of our sequence an must equal 0 also. So therefore we can say that the sequence an converges to 0.